Hi everyone, I'm Emily Shroyer. I'm a physical oceanographer at Oregon State University. I'm interested in studying ocean physics at the interface of other components of our climate system. I've been working quite a bit at low latitudes, looking at air-sea interactions. I also work at high latitudes, looking at how the ocean and the ice interact with one another. I'm interested in studying the interplay between small scales, and by that I mean turbulent mixing, and how turbulence influences larger circulation patterns in our ocean. I do this typically using a combination of observations and models. However, since this is a lightning talk, I'm going to talk to you about just one of the things that I do, and that's how we go about measuring turbulent mixing. So one of the first things you do when you add milk to your coffee or use tea in the morning is you take a spoon and you stir it. And when you do that, you're injecting a little bit of kinetic energy into the system, and that kinetic energy is leading to turbulence. And you see lots of eddies and stirring motions when you mix your milk. But eventually that turbulence creates an environment where molecular diffusivity can work very effectively and lead to actual mixing between your milk and your coffee. One way of visualizing that process is if we take this little pink patch of fluid in the sketch here and we start to stir that pink patch of fluid with all the red arrows. We strain and stretch and pull the fluid out, and in that process, we not only increase the surface area in contact with the ambient fluid, but we also enhance the gradient between the pink fluid and the ambient fluid. And when we create a state with enhanced gradients and high surface area, those two properties can lead to enhanced molecular diffusion and mixing. Turbulence is associated with a range of scales. It typically has eddies associated with starting sort of around the few millimeter scales where molecular processes are starting to work, and ranging up to tens of meters, which are the energy containing scales, and closer to where turbulence is forced. Turbulence is highly intermittent. It is a property of the flow. It depends on what the circulation is and how the ocean is being forced. And because of that, one of the only ways we can actually quantify turbulence is to go out and actually measure it. One of the ways that we measure turbulence is with a microstructure profiler. One such system is shown here. This is Oregon State's system, the Chameleon Profiler. It's being thrown off the back of the ship. It'll be lowered through the water column. It's actually falling freely through the water column. And then when we get to sort of where we want to stop profiling, we'll pull it back up to the surface and then let it drop again and repeat the process. At the nose of the microstructure profiler, there's a few very specialized sensors. You can see those in the center bottom here. Microstructure profilers typically have fast thermistors, the little beads at the top of the system, thermistors labeled. This is measuring temperature fluctuations at 100 hertz, very small scale fluctuations very rapidly. And the other sensors you see here that look like the white points, those are shear sensors or airfoil probes. They are essentially record player needles. And as the system is dropping through the water column, the record player needles are deflected back and forth. We measure those deflections, and from that, we can calculate the turbulent shear in the water column. The set of panels is showing microstructure data. The one on the left shows you the shear fluctuations. The middle panel is showing turbulent fluctuations associated with temperature. And the last panel is showing the conductivity signal in turbulence, which is essentially showing you a measure of salinity. And if you'll look at the depth scale, all of these little wiggles are occurring over a distance much smaller than a meter. So those are the types of scales that we need to measure if we want to understand turbulence in the ocean. So the microstructure profiler is just one of the types of platforms that we measure turbulence from. Another quite common way that turbulence is being measured now is from gliders, that's shown in the upper left. The upper right is showing you a towed body, which is pulled behind a ship and measures turbulence over broad lateral swaths. The sensor package in the bottom right, along with the two sensor zoom ins here. This is showing a moored temperature package. So these can be put out on moorings for over a year, and you can get a time series of mixing at a particular depth over a long time period, which is very helpful considering how intermittent turbulent events can be. Turbulence is also measured through dye releases, through acoustics, and really using a variety of means to try to understand how mixing infects our ocean. Okay, thanks everyone. Have a great day.